Alright, as it turns out, there is a matrix that behaves like 1, where if we multiply it by another matrix, the matrix remains unchanged, and this is what we call the identity matrix. The identity matrix must be a square matrix. It has to be n by n. So you can't have a 2 by 3 identity matrix. You can only have a 2 by 2 or a 3 by 3 or a 4 by 4, etc. It must be square. So if I wanted to illustrate the, say, 3 by 3 identity matrix, we're going to have 1s along the main diagonal and 0s elsewhere. So the 3 by 3 identity matrix would look like 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so that would be the 3 by 3 identity matrix. The 2 by 2 identity matrix would be 1, 0, 0, 1. There we go. So there is no single identity matrix. Different sizes have a corresponding identity matrix. Now, if you want to, go ahead and verify this using your calculator. So take, any matrix, say maybe a 2 by 2 matrix. If we take 1, 2, 3, 4, and you multiply that by the matrix 1, 0, 0, 1, it will give you exactly 1, 2, 3, 4. The other thing to note about the identity matrix is it doesn't matter which side you multiply on. So if we did 1, 2, 3, 4 times the identity matrix, or if we swapped the order and we did the identity matrix times 1, 2, 3, 4, we still would get the same result. So the identity matrix is like 1 for matrices, but it has to be a square matrix. Now, the other nice thing about the identity matrix is that we can use the identity matrix to perform row operations for us. So, for example, if I would like to interchange 2 rows in a matrix, I can interchange those equivalent rows on my identity matrix. So if I wanted to interchange row 1 and row 2, I could rewrite my identity matrix with row 2 as the first row and row 1 as the second row, and row 3 would remain unchanged. So this has swapped row 1 and row 2. So let's see how we can use that given the example that we have below. So let's go ahead and solve this, the system represented by this augmented matrix. Remember, we can imagine there's a vertical line right here. So we have a 3-variable system of equations. Okay, so let's see. The first thing that we would like to do as far as our row operations go, we have a leading 1 in the first row. We already have a 0 in the second row, so now we need a 0 in the third row. So we would do 2 times row 1 plus row 3. And this would go into row 3. Well, let's see how that row operation looks on the identity matrix. So if we take our 3 by 3 identity matrix and we apply the same row operation. So I'm going to do 2 times row 1 plus row 3, and this will go into row 3. Well, row 1 and row 2 will remain unchanged, so we will have 1, 0, 0, 0, 1, 0. But now I have 2 times row 1 plus row 3, so that would give us 2, 0, and 1 in the bottom row. So how do I use this matrix in conjunction with my augmented matrix that I already have? So to perform the indicated row operations, we will multiply our augmented matrix by this augmented identity matrix, 0, 1, 0, 0, 0, 1. Notice that we have to multiply it in the front, and that's so the dimensions match. So there's no way that you can multiply this in the wrong order because the dimensions shouldn't match. Okay, so we'll go ahead and perform that row operation using our calculator. So we're going to do the matrix multiplication. So you want to use your calculator and do your matrix multiplication, and this gives us a new matrix, 1, 0, 0, 4, 2, 13, 2, 8, 10, and then our constants are 3, 8, and 10. This is exactly what our original row operation was trying to do, right? Our goal was to make the -2 in the first column a 0, and that's exactly what we did. Except that now, instead of having to do the row operation by hand, we were able to use matrix multiplication to do the row operation for us. We can also use this to do lots of row operations at once. So say we wanted to divide row 2 by 2 and then add it to, combine it with rows 1 and rows 3, we can do all of those operations in one of these adjusted identity matrices. And so that makes it a little bit easier to do, to solve systems of equations in this way.